Okay, welcome back, everybody. And the topic this week is to continue our discussion of full configuration interaction theory, which, as we said, in principle, means that if you can solve the problem, if you can diagonalize this Hamiltonian matrix, you have essentially solved the problem. Now, the problem is that the dimensionality quickly explodes, and that means that the dimensionality of the matrix you want to diagonalize quickly becomes unwieldy. It means that if you have, let's say, 1 billion of Slater determinants, you would have to invert a matrix, diagonalize a matrix, which is a 1 billion times 1 billion. So the typical limit for what we call full configuration interaction diagonalization methods is roughly matrices of the size of 10 billions times 10 billions. You're not going to diagonalize 10 billions times 10 billions, but you're going to use iterative methods to find the eigenvalues. And some of these iterative methods, they converge to the lowest lying and the highest lying states. And there is a method which is called Langsos's iterative method, which is a way to obtain the eigenvalues and eigenvectors by diagonalization. And that falls under the largest subset of methods called Krylov methods. Now, what we are going to do is to set up the formalism and remind ourselves about some of the notation which we introduced last time. And then with that, we are going to set up the equations. And when we have done that, so full configuration interaction theory is perhaps the simplest many-body method we can think of mathematically and also setting it up. However, it's limited by the dimensionality. So when you want to attack much bigger systems, we have to go beyond the diagonalization and look at approximative methods. And that will lead us, which is something we will start with this week, is mean field methods. And then Hartree-Fock theory is actually one of these methods. And that's where we will try to end this week by starting with a description of mean field methods. And density functional theory, which is extremely popular in quantum chemistry, condensed matter physics, and many, many other disciplines, is a method which we will also discuss when it comes to mean field methods. But now we are going to remind ourselves a little bit of what we did last week, just a quick repetition. And then we are going to look at the equations which we end up with. And after we've done that, we are going to look at a diagrammatic representation of the same things. But we will also look at a little less practical way of solving the equations. And the reason why I do that is that that will link to other methods. So let's just remind ourselves a little bit about what we did last time. So we have a ground state, which we have assumed. So I'm going to use the acronym GS for the ground state. So when you see that one in my notes, this stands for the ground state. And the ansatz which we made is an ansatz based on us filling up all the states up to the Fermi level, the single particle states. And we have the creation operators, and we use these indices subscript I, and J's, etc., for states below the Fermi level. And this now acts on the true vacuum state. Then what we could do is to define a one particle, one hole state, which is just another way of distributing the single particle states. And we put a subscript I to indicate that this is a state below the Fermi level, and a superscript A to indicate that that's a state above the Fermi level. And this is something which we then would write as an A creation operator. And then we annihilate a particle below the Fermi level. So this operation here takes out one particle below the Fermi level. And here we have assumed that I is included as a single particle state in phi 0, whereas A is a state above the Fermi level and is not included in phi 0. So that means that we create what we have been calling a one particle, one hole excitation. So it's just a way of relabeling all the possible ways we can distribute particles in single particle slots. So that was a one particle, one whole state. And then obviously you can continue along these lines and you can create a two particle, two whole state. So if we just move on a little bit, we can have a two particle, two whole state. And in that case, we would label that one with an IJ to indicate that we have two vacancies below the Fermi level. And then we have shuffled these two particles above the Fermi level into two new slots. And this is something which we would rewrite as an A. And since these are fermions, we have to make the operator here for the two particle, two whole state to be anti-symmetrized. So that's why we interchange the J and the I here. And then this is acting on phi 0. So we are looking at excitations around this specific vacuum state. And then you could continue with free particle, free hole, etc., etc. So another thing which we did last time was to rewrite the Hamiltonian in terms of three terms. So let me quickly remind you of that. So we have the Hamiltonian operator, which we rewrote in terms of a constant, which is what we call the reference energy. And I'm going to just to quickly remind you of what these are. So I'm not putting a hat on that one because that's just a constant. And this E0 ref is simply the expectation value of the Hamiltonian with the ansatz for the ground state. And this is something which we calculated in the very beginning of the semester. And we can write this one as a sum over all the states below the Fermi level, where we have a one-body part of the Hamiltonian, plus 1/2, and then we have a sum over all a double sum over all the single particle states below the Fermi level. And then we have a V, and then I and J. And we can write this out in a more compact way in terms of these anti-symmetrized matrix elements. So that was the reference energy. Then, when we have defined a new vacuum, we rewrote the Hamiltonian in terms of a Hamiltonian which is normal ordered with respect to the new vacuum. And the one-body operator, this F of n, is then something which we rewrote like a free sum over all the single particle states. And we have the integral over an operator F, which we are going to define again here. And then we use this symbol to indicate that the curly brackets to indicate that this is a normal ordering with respect to the new vacuum. Now, after this equation, I'm going to take away the curly bracket because from now on, we are going to look at these operators as normal ordered with respect to the new vacuum or the new reference state, which is a better way to label it. So this operator then has this integral, which we, after the manipulations we did last week, we could rewrite this integral as, so we have a P of F of Q here, and this is the same as the integral with the H0, the one-body operator, plus, so we can put a hat on this one, plus a sum over states below the Fermi level. And this gives what is called a mean field contribution in the sense that a particle in a state P sees the effect of all the particles below the Fermi level. And this has the interaction itself. And then we have a Q of J, like that. And we would typically put an AS here because we use anti-symmetrized matrix elements. Then the final part of this rewriting of the Hamiltonian with respect to a new reference state is now given by the two-body matrix elements if we now stop at the level of a two-body interaction. And this contains now a new integral, PQVRS. This is a two-body integral. And then we had the operators. So we have an AS here, and then we have an AP dagger, AQ, AS, AR. And this is the anti-symmetrized matrix elements or integrals. So from now on, unless it can be misunderstood, we drop these curly brackets. So it's understood that the operators are normalized with respect to the new reference state. And what we are going to do then is simply to rewrite this PQVRS anti-symmetrized. I'm simply going to replace that one with just PQVRS. And then that means that depending on what we have in front here, if there's a factor of a half, which you will see in many textbooks, if there's a factor of a half, then it's not an anti-symmetrized element. If there is a 1 over divided by 4, this means that we actually include the direct term and the exchange term. So from the context and the way the equations are written, in order to avoid notational clutter again, we skip AS and we also skip these curly brackets. So I will obviously repeat that now we are looking at the states with respect to the new vacuum, and also that the integrals are given by anti-symmetrized terms. That means we have both the direct and the exchange term. Is that okay? So this is just to avoid all these kind of subscripts, which sometimes you tend to forget. Now, the thing which we did last time was then to expand, since we have a basis of Slater determinants. So when we start the semester, if we now look at the ground state as an example, so when I use the letter psi, uppercase psi, I'm normally referring to the exact state, or the best possible representation of the exact state. And what we did then was to write this out in terms of an expansion of Slater determinants. So in principle, this starts from 0 and it goes to infinity, but we will put a letter m, which now is an approximation to infinity. And then we have the overlaps, C lambda, and then we have this basis of Slater determinants. This is the way we wrote it in the very beginning. And then we have a basis of Slater determinants, which is orthogonal and normalized. And then we have a delta here. So that gives us just a Kronecker delta, lambda delta. And then clearly the coefficients are given by the overlaps between psi 0 and phi lambda. So what I should say as a kind of intermediate step is that essentially all we do in different many-body methods, if you want to keep this picture, is actually to try to find either exactly or an approximation to these coefficients. So when we are going to go beyond full configuration interaction theory, where we get these coefficients, when we diagonalize what we are going to label as the Hamiltonian matrix, then the different many-body methods, whether we do perturbation theory, copper cluster theory, which is widely popular in quantum chemistry, they will represent approximations to these coefficients. And I will try to elucidate that today when we are looking at a clumsy way of solving the full configuration interaction diagonalization problem. So hopefully that will come through. So this is just some kind of technicalities which we are anticipating. So if you have obviously solved the problem, it means you have these coefficients, and then there is no point in continuing. The problem which we have is that the problem is has such a high dimensionality that we have to make approximations. And hopefully these approximations are controlled, so you can easily expand upon them in a systematic way. So if we now look at this expression here, what we have done, so let's just put this as an aside. What we have done is to rewrite this in terms of a new way of reorganizing the Slater determinants. So we define this in terms of particle hole excitations, and then we have the states phi HP, and where this phi HP is given by some operator, H multiplied with phi 0. And this operator here could be, if we have a one particle, one hole case, then this is given by AI acting on phi 0. So that would be a typical example if you have a one particle, one hole case. So when you see this generic one with an uppercase letter H and uppercase letter P, this is just going to represent a given type of particle hole excitations. It could be 0 particle hole, it could be 1 particle 1 hole, 2 particle 2 hole, etc. So this is just an example of what this looks like. And then for this specific case, this one turns into CIA. So these are just notations which we introduced last time. And when you then rewrite the operator, this AHP, what you can do then is to write this out in terms which involve 1 particle 1 hole, 2 particle 2 hole, etc. So let's just write that down. And let's just wait a little bit till everybody have been able to actually write it down here. So this is an expansion. When you look at this one, you could apply this to any state of the system. This is not limited to the ground state, but I'm just using the ground state as an example here. So let's take a closer look at what this may look like. So we would then rewrite it like this. So we will have a coefficient which is just called C0. And then we have phi 0. That's the first term. And then we have the next terms, which go like a sum over I and A. And then I have a CIA. And then I have my state, IA here. And then I get a state now, which has so this is the 1 particle 1 hole. And then I have the next one, which is going to be a 2 particle 2 hole state. And that has coefficients Cij and AB. And then I have a state, which is given in terms of 2 creation and annihilation operators. And this just continues all the way to the final one. And the final one is something which I'm going to sloppily just write like n particles and n holes. And we are going to have a coefficient Ci1, Ci2 up to Cin. And I'm going to have an AI, this is a particle state, A2 up to AN. And this is in turn multiplied with a state function where I'm just going to write NP and NH like that. So this is the same as NP, and this is an NH. No, sorry, the opposite. NH and NP. So with n particles, we can make n particle, n hole excitations. And that is this one. And the one you see here is a 2 particle 2 hole. So that means that in here there are 3 particle 3 holes, 4 particle 4 hole, and up to n particle n hole states. So this is often rewritten in terms of an operator. And you will see it in the literature. You will see something like a C0, which is a constant. But then I'm going to define an operator which has a name in the literature, and it's called the correlation operator, because that brings in correlation from all the other states into the ansatz for the ground state. So if I were only to keep the ground state ansatz, then clearly I would only have this term plus that term. But then I'm mixing in contributions from the other configurations, and they bring in correlations in the setup of the total wave functions. So we are correlating different Slater determinants through the Hamiltonian matrix, through the Hamiltonian operator. So this operator C is now a sum over, if we just write it in more detail, it's an operator. It has these coefficients. It has AA and AI plus, and then there is a sum over AB, IJ, and then I have the coefficient Cij, AB, and then I have creation and annihilation operators. And this just continues plus plus. So what we are going to make now is an intermediate simplification. And you will encounter that in the literature. And it's called intermediate normalization. And I'm going to explain to you what that means, because that will allow us to put this coefficient C0 to 1. And that means that you will reshuffle the strength in the normalization process into the other coefficients. So it's called intermediate normalization. And the assumption we are going to make now is that this C0, that's the first assumption, is different from 0. And the normalization, so let's just write this down. The normalization of the final state of psi 0, or any state which we're expanding in this one, is in principle at our disposal. There is nothing magic with the way you normalize things. And that means that you may arbitrarily, so since it's at our disposal, we may then, and I'm just writing down this text, we may then arbitrarily, and that simplifies the notation a lot, well, it's set this C0 to 1. Let's just do that. And that means that corresponding to proportional changes in all other coefficients, which then corresponds or leads to, proportional or corresponding, it should be a 2 here, to corresponding proportional changes in all other coefficients. CHP. So that means that what we are going to do now is to say that psi 0 of phi 0 is going to be equal to the norm of phi 0 with itself. And we put that one, so this is C0, and we just put that one to 1. So we would then have psi 0, which is equal to 1, plus this correlation operator acting on phi 0. So this operator, which you see here, this one, is normally called the correlation operator. So let me just write it out here. So this is the correlation operator. Like that. So these are kind of notations which we will carry with us. But let's now look at the diagonalization problem itself. So what we are going to look at is obviously solving the Hamiltonian problem. So with that kind of expansion which we have chosen, the one here, this specific expansion, we can now set up the Hamiltonian problem. So let's try to do that. So the Hamiltonian problem which we want to solve is obviously us acting on this state, for instance, and that gives us E0. But keep in mind that we could have any state. So when I'm using this E0, this is now going to represent the exact ground state energy, and psi 0 is going to represent the presumably exact eigenstate of the ground state, okay? So if we now look at the formalism which we have put up, we can actually rewrite this as E minus E0. And then this is going to act on this summation over particle Hall states, CH, P of phi, H, P here, okay? That means that if I now look at the matrix, the expectation value of the energy, so if I multiply with the psi 0 from both sides, what I'm getting then is the following. So I will then have a summation, and keep in mind that the basis I've chosen of Slater determinants is an orthogonal basis. So if I multiply with that one from both sides, I'm going to get an expression here where we're going to have a sum of a pH and pH prime, like that. And we are going to have now a phi h p, and then I have my h minus E0. I should remember to put hats on here. And this is multiplied with phi of h prime of p prime. I have now the coefficients, and I have to put a star on this one because this is the complex conjugate. And then I have a ch prime of p here. Now, we know very well that these states, which we have set up, these are orthogonal states. So this obviously leads to the following expression. So that leads simply to, and this has to be equal to 0, obviously. So we would get a sum of a pH prime, and then I'm just going to put in the elements here, ch of p, complex conjugate, and then a ch of p prime, and then I have phi of h of p, and then I have the Hamiltonian here of phi of h prime of p prime, and this has to be equal to E0, and this is multiplied with P of H of CHP, because now we are using the orthogonal properties of the basis which we have. And this equation here, obviously, when we now shuffle it over, this equation here, when we look at it, it should obviously be equal to 0. So the only thing I did then, I should put an arrow here. Sorry for that, I forgot that. Because what I'm doing then is simply to put E0 on the other side of the equation. So this is, when I multiply with phi 0, this has to be equal to 0. So I forgot to put that one. I should sneak it in here. So this is equal to 0. And then I simply reshuffle E0 to the other side. Now, some of you may actually be familiar with Lagrangian calculus and the type of variational calculus. So you can actually rephrase this in terms of you introducing a variational calculus parameter with a, so I don't know how familiar you are with that. If you've taken a course in classical mechanics, you have probably encountered these topics. So I'm just going to put that as an aside. So this is equivalent what we are setting up now to a variational minimum. We are coming back to that when we are looking at Hartree-Fock theory, to a variational minimum, where we now have a problem like this, psi 0, and then we have a Hamiltonian here of psi 0 minus a parameter which is called a Lagrangian multiplier, which you have due to the constraint of orthogonalization, and obviously we want it to be normalized. So in this specific case, this parameter is called a Lagrangian multiplier, which is a constraint you bring in because you have some variables which are not fully independent, because you have a constraint on the wave function that it has to be normalizable and orthogonal. So this is called a Lagrangian multiplier. So the problem of setting that up is actually equivalent with that, because the minimization then, so let's just continue. So it is not so important for us now, but we are coming back to that when we look at Hartree-Fock theory. Minimization gives then, so we are changing the wave function. So we are going to require that by changing the wave function with a minimum variable, psi 0 of h of psi 0 minus this lambda, and then we have the psi 0, if this should be equal to 0, and that is going to give rise to the same type of equation which we had. So I'm just mentioning this because what we end up with is actually a diagonalization problem at the end. Now, if you look at the equations which we have, so let's go back a little bit. Is everybody okay if I just move back one? So if you look at what you have here, or the equation which you have here, this is something which we would typically rewrite in terms of a matrix eigenvalue problem. Okay, so let's just look at that. So this is essentially the equations which you want to solve, and this is equivalent with you finding the characteristic polynomial of a determinant which is given by the Hamiltonian minus the eigenvalues. But let's now look at the practical implementation of what we are going to set up. So if you now look at the equation which we started with, this H acting, let me just rewrite it like this. So we have H acting on a state, and this is equal to some energy, E0 times some psi 0. Now, this equation here, when we now collect the different parts, is actually an equation which reads, we have a sum of pH, and then what we have here is a Hamiltonian, so we have a CH of P, and then we have the Hamiltonian acting on this state, this series of state of H of P, and this is equal to E0, and then we have the sum of pH, and then we have CHP here, like that. Now then, multiplied with this phi H of P, like that. So one thing we can do now when we are setting up what's called a Hamiltonian matrix in order to look at or study this problem which we have here, this one, what we end up with is, if we now multiply from the left with phi 0, so this would correspond to a block or a part of the Hamiltonian matrix which we have, and then we can multiply it with a one particle, one whole state, etc., etc. So let's just write out these different terms. So let's look at what happens when we multiply this equation here from the left with phi 0, because doing that, what we are setting up now is to multiply with P of H prime, and then we are multiplying with all the states which we have here, PH prime, and then we have a CH prime, and this is a complex conjugate quantity. So let's now look at this term by term. So first we take this equation which you see here, and we multiply with this phi 0. Let's do that, step by step. So the first term is going to give us now phi 0. And this is multiplied. If we now just stick to the equation, we can now write it out in terms of a left-hand side and the right-hand side here. If we do that, then we have H, and we're going to have a sum here over PH, and then we have this phi H of P, and then we have the coefficient CHP, like that. And this is equal to E0, which we can single out here. And then we have the sum over pH, and we have the coefficient CHP, and then we have a coefficient here which gives us phi 0 times this phi H of P. Now we know that this is an orthogonal basis, so this is just going to pick out phi 0. So that will contain the first coefficient, which we called C0. So if you now look at this expression here, this represents now, if we write it out term by term, if we take the left-hand side, what we are going to have then is the following. So we will have a first term, which is just phi 0. And then I have H, and then I have phi 0. That's the first term. And then I'm just going to reintroduce C0, which we put to 1 using intermediate diagonalization. But let's keep it like C0 now. This gives us now the next term, which is phi 0. And now we should be a little bit careful here, because this is a sum over all the particle hole excitations. And we have H, and then we have phi of IA, and then we have the coefficient CIA. We have plus, and then we have AB, IJ, and then phi 0 of H, and then we have phi IJ of AB, and then I have a CIJ of AB, and this continues all the way up to n particle n hole. So I'm going to have n particle n hole excitations, and I just write this in a little bit sloppy way here. And this is equal to E0 times C0. So this is something which we now can write out in a little bit, how to say, sloppier way or more compact way. So I'm simply going to, if you now think of this as you setting up a Hamiltonian matrix problem, which we have here. So if you look at the coefficients which you're getting, this one would now correspond, this term which you see here, this would correspond to integrals of the type between phi 0, and I write it like H, and I'm just going to call this for configuration type 1. And similarly, so this is actually one here is a block of one particle, one hole, and I'm going to indicate that I actually wanted to bring it. So I'm going to label this one as a one particle, one hole. So this is a block of states, because you see that you have a summation here. So that represents a specific block of states. And so the whole thing here is actually now going to be this specific guy here multiplied with a specific coefficient, which I'm also going to label as just a C, one particle, one hole. So I'm going to write this out like this. So I'm going to have this as, so this is going to be equal a, if I call this now for H 0, 0. So this is going to be H 0, 0 times C0. And then I'm going to call the next one for H 0, 1 multiplied with C1. And this is going to represent this whole block of phi 0 of H with phi 1 pH, one particle, one hole, C, one particle, one hole. I'm trying to find a more compact. So this 0 and 1 now means a whole block of matrix elements, but I'm writing them in a more compact way, where I have all the one particle, one hole coefficients. So it's a kind of more compact notation. And then I'm going to get an H0, 2 with C2 here, where this is going to be all possible contributions with two particle, two hole. And this one is going to be all possible C, two particle, two hole coefficients. Then if we continue like this, when you see number 3, that's going to represent the block with 3 particle, 3 hole guys, etc., etc. So it's just a compact notation. So I'm going to have this one, which is H03 of C3 plus, 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 and then I have H0, and then I have N here, which is N particle N hole times C of N, and that has E0 times C0. So that's the my first line, which comes through by multiplying with phi 0. Now you can repeat that again, and now you can multiply the same equation which you had here, the equation which, if we go back, so what I did was to multiply it with this one. Now I can multiply it with this state, and so on. So what you get then, and this is the kind of compact notation, so now I'm going to have the one particle, one hole block, which I've just labeled as 1 here. So I will have now a H10 multiply with C0 plus 1, 1 with C1, and this goes all the way up to H of 1n times C of n, and it has this eigenvalue C0, C1. Then, if you take the two-particle, two-hole block, you're going to get terms which go like 1, 2, 0, C0 plus H 2, 1 of C1 plus H of 2, 2 of C2, and this goes all the way up to H of 2n times Cn, and this again equal to E0 times C2. So this object actually represents, as I said, blocks of integrals, and the coefficient C now represents blocks of coefficients. So I'm just writing them in a very compact way here. If you now look at what you have, if you look at these equations, these are the left-hand sides. The left-hand sides are things which you can rewrite out in terms of the following. So I'm now going to the general expression here, where I now am putting a subscript j, which now runs from 0 particle 0 hole up to n particle n hole, like that. This is now going to be given by what we will call a matrix, or the Hamiltonian matrix. So this will have an index I, j, times a vector. So this Cj is a vector now, and that is equal to a specific eigenvalue, E of I, times a vector C of j. So what are we doing here? No, sorry, C of I. That is wrong here. So what you have is actually an eigenvalue problem, where you now have a matrix, so this Hij. So what we have rewritten here is actually a matrix times a vector equal to an eigenvalue times a vector. So if you look at this case with E0, this is the general expression for it. But this case which we wrote down here is something you could now rewrite as a matrix, which is H00, H01, H02, where now these are blocks with many contributions in each of them. Just keep that in mind. And then we have H0n. This is now multiplied with these coefficients, C0, C1, C2, and all the way down to C of n. And obviously I have H10, H11, this goes all the way up to H1n. And finally I have H of n0. This goes all the way up to H of nn, like that. And each one of these is now U. So each one of these Hij are actually given by one of the blocks which we have. So I can take a phi I of H of phi j, where these can be different n particle, n hole excitations. I put prime here. So I haven't specified whether this is a 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole, etc. So these are the explicit contributions. If you go back to the expressions which we put up here, we have terms like these. What I did now was simply to multiply from the left the different parts here. So what I did here was to take Schrödinger's equation, which we have here, and simply multiply it with these terms. That way, I'm building up a set of equations where I now have the different contributions from the different particle hole terms. And this sets up what we call the Hamiltonian matrix. And probably this is something which you have seen in some of the basic quantum mechanics courses. Now, this is again, for this specific case with the eigenvalue which we looked at, this is going to be equal to E0 times this vector C0, C1, and keep in mind that each one of these C's here can then represent the contribution from a block with many different types of slated determinants. So in principle, this is something which we then would rewrite like H, which is now a matrix, times a vector C, which is equal to an eigenvalue times a vector C. That's a general expression. You want me to go back one page? So this is so what I did now, if you look at these expressions, if you collect all these terms here, all of them, then you can rewrite the left-hand side in terms of this matrix multiplied with these coefficients. And then you have the eigenvalue, and then you have the vector again. Yeah. So here it's a generic one, right? Because this, in this case, I just picked E0. So that means that the coefficients you get will be different from each eigenvalue which you look at. So this would be the generic expression which you set up. And the way you will often see the generic expression written is like this. And then you would put subscripts like state I, eigenvalue I, and the state I. But what we actually have done is simply now to rewrite the problem now in terms of an eigenvalue problem. And where these matrix elements actually represent overlaps between different states. So each one of those matrix elements which you see here now, like this one, if you pick that specific state, that is actually phi 0. And we have already calculated that one with H and phi 0. This specific state here would now be phi 0 with H and then phi of a two-hole and two-particle state, etc., etc. Now, in principle, since you have an infinity of single particle states, you could have an infinity of two-particle, two-hole slated determinants. So that means that every contribution which you see here, like this one here, or that one here, can contain an infinity of contributions. But we will obviously shrink down the number of single particle states to a set of states which we can handle. And that means that every one of these will be a vector of limited length if phi 0 is degenerate. But you could also think of that as just one number. So if you have one particle, one hole state, this is just a number. It's just the integral which you see here. If you have one two particle, two hole state, that is a number. But we can just think of this generically as blocks of states of a two particle, two hole, three particle, three hole, etc. character. So that means that the full configuration interaction theory is if we can set up these so-called matrix elements and you can diagonalize, then you have essentially found the solution to the eigenvalue problem, which is this one. So this is full configuration interaction theory because it's called full, because we take into account all the ways you can distribute the particles. So it means you take all slated determinants in that basis of single particle states, full. Configuration, because one configuration is one way you distribute the particles. And interaction, because you let these configurations interact through the Hamiltonian. So this is the root of the name full configuration interaction theory. Okay? And you see now that the only thing you need to do now is to go back to the exercises from week 36 on the Condon-Slater rule. And then you can immediately set up what these different matrix elements are like. And then you can set up, because these are many-body states, and you're calculating overlaps between different many-body states. Does that make sense? The way we've been setting it up? I'm going to use this one to show you a clumsy way by which we can solve the eigenvalue problem by iteration. because that will link to other many-body metals as well. I went a little bit over time, and I'm going to repeat some of these things after the break, but I think you guys deserve a small break now. So what we're going to do now is to break this down into the explicit terms which you can obtain if you now look back at the compact, very compact formalism which we put up here. What we're going to do now is actually to look at some of these matrix elements and break them down and see what their values look like. So last week, we did actually calculate some of them. So suppose now that we break this down. So this is just a generic eigenvalue problem. And the way it's written here, it is any of the eigenvalues. And then you would have every such set of coefficients corresponds obviously to one eigenvalue. So normally these coefficients would then be stored as a matrix themselves, because that would be a coefficient which corresponds to this eigenvalue. And then there is another coefficient, set of coefficients, which corresponds to another eigenvalue. And then you would typically store these in terms of, so this would be a 0, 0, 0, 1, etc. And you would typically store these, actually all eigenvalue programs, they return these coefficients as a matrix. So the problem here, if we can solve it, then we're basically done. But as I said, the dimensionality explodes quickly. So let's look at what these elements look like. So one of the elements which we defined was this H00, which actually is I0. So this is the expectation value of the ansatz for the ground state. And we have calculated this one already. And we know that this one is something which we can easily look up. So if we have tabulated these integrals, so the first integral is this one. And often we choose the single particle basis to be an eigenbasis of H0. In that case, this just transforms into a number, just a plain number, which could be like the energy of a harmonic oscillator. It is an integral, so it's obviously just a number, but in many, many cases, this simplifies further. So we could just look up, let's say, the eigenvalues of a harmonic oscillator or the hydrogen atom or whatever. And then we have the next term plus this factor 1/2. And then we are summing over all the single particle states. And remember now that when I write it like this, I am meaning anti-symmetrized integrals with a direct and exchange term. So this is a matrix element, H00, which we can look up immediately if we have it tabulated. Then this H01 corresponds to us having taken the overlap between a one particle and one hole state. So this is a one particle and one hole. And a typical example, when we look at that, if we now just specify the states to be I and A. So this is something which we calculated last week. And we found that this is equal to these overlaps or integrals between a single particle state A and a single hole state I. And this is something which we can also tabulate. So this follows from the exercises we had in week, I think it was week 36 on the Condon-Slater rule. Another element which we could look up, which we also calculated last week, is H02 here, which is the overlap between the ground state ansatz and a two-particle, two-hole state. And we did calculate these ones as well. So if we take a specific example of a two-particle, two-hole state with the two holes from single particle states I and J, and two particles in states A and B. So this is a two-particle, two-hole guy. This is something which we also could calculate. And this was given by the integral AJ, AB, and we can put anti-symmetrized here. just to remind you that these are anti-symmetrized terms. So this is also something which we could look up. So if you have been able to calculate these integrals, you can always tabulate them. And then when you look at this specific Slater determinant or state, you know exactly which single particle states are being changed to particle states. So which whole states you are starting with and which ones you are creating here. So that means that you differ by 2 single particle states here and in the ground state ansatz. And then you can just, from the Condon-Slater rules, you can just set up a formula with where you're broken down and found the indices I and J and A and B. Alternatively, you can calculate these on the fly when you're setting up the matrix to diagonalize. Now, one thing which we also discussed last time was the case where we have a free here, which is the overlap between a free particle, free whole state. Now, the assumption we have made is that this is at most a two-body operator. If you now go back to the exercise in week 36, this has a very simple value. Does anyone remember that? Yeah, that's 0. So as soon as you have more than 2 single particle states which differ on the Brown-Niket side, then this specific integral has to be 0. So remember now that there's one thing I want you to keep in mind here, because sometimes we can be deceived by the fact that when you look at the integrals, you have only the single particle states. But that is because an overlap here, or a transition matrix element, as we sometimes call it, or an overlap, or just the integral, is taken between a many-body state on the Bra side and a many-body state on the Ket side. But due to the way we have set up these ansatzes, this breaks down to integrals which just involve single particle states. That simplifies a lot the machinery. Because else, these are in principle, this one here, they are integrals. If you have 10 particles in 3 dimensions, these are 30-dimensional integrals for every single particle state. No, sorry, for every state here. So if you have 10 particles here in 3 dimensions, then you're actually calculating a 30-dimensional integral. But now this reduces and simplifies because we are using these single particle pictures and ansatz to build up many body states. So that means that this one, as we said, is 0. And that means also that H4 is 0, H0, 5, and then that continues all the way up to H0 of n particle n whole, where n, this n here, is different from 2, larger than 2. Now then, we could continue with the next case. If you go back to the, sorry, if you go back to this Hamiltonian matrix, we have assumed that this is a Hermitian operator. That means that these guys will be the same. Here, we would need to calculate explicitly matrix elements, and that's going to be an exercise later. So what you would need then, if you now look at one of the coming blocks, if you look at this H11, that is simply a 1 particle, 1 whole state. So I'm just going to write it like this, and 1 particle of H, and then a phi of 1 of H prime, and 1 of P prime. So that could be, as an example, it could be an integral which involves I and A. And then I have a phi of J and B. So these are things which we haven't evaluated yet, but we can use the same rules as we used last time with this normal ordered Hamiltonian with respect to the new vacuum. So we are going to leave that as one of the exercises for you. And this is not necessarily equal to 0. However, if I now take 1, 4, that is going to be, as a typical example, it would now be a 1 particle, 1 whole state. And then I would have a 4 whole and 4 particle state. And an example here could now be phi IA again. And then I have the Hamiltonian. And then I have a phi of K, L. And then I should put a J, not K, L, M, N. And then I could have now an B, C, D, E as a state here. Now, if I have a two-body operator only, this matrix elements, or this contribution to the matrix, takes also simple value. Anyone who sees that? Yeah, 0 immediately. So as we said, there are going to be many, many zeros. So it means that when we now collect and put everything back into order, we are going to have a Hamiltonian matrix here, which is now going to look like as follows. So we will have something when we now set up the matrix. I'm going to bring it back here. So we have, here we have H. So let's just write it in a compact way here. So this would be 0, 0. Then we have 0, 1. And then we have 0, 2, 0, 3, and all the way up to 0, n. And then down here we have 0, 0. We have 1, 0. We have 2, 0. And that goes all the way down here. Now here we have an explicit value. This is non-zero. Here we also have an explicit value, non-zero. And then all the other ones are 0. And here we have non-zero. And then all the other ones are 0. And here we have non-zero, non-zero. This can be non-zero, but this has to be 0 because then we have more than one set of single particle states which are different. So this goes down like that. And then we have zeros. And then we will have X, X, like this, and then zeros. And as we discussed last time, what we are going to see then is that this will be a sparse matrix. So we will have zeros here, and then we have matrix elements which are different from 0 along this one. So this is going to be the Hamiltonian matrix, which we then can set up and diagonalize. Now, I want to bring in some further notations here, because that's going to lead us now to what we normally call post-mean field methods. And I'm going to link approximations, which we are going to make pretty soon. So if we look at this first row here, because what we did then was to multiply this one with a set of coefficients. And I'm just going to write the coefficients like this. So these are the different coefficients. And this is equal to a specific eigenvalue. And then we have this coefficient C again. So if we can diagonalize, obviously we have the expansion parameters of the wave function in terms of a Slater determinant basis. So let's now look at the first row again, because this is something which we are now going to use to define some specific quantities. So let's take this row here and simply take this one and multiply that with a vector here, okay? So let's set up the kind of equations which we can get now. So we have the equation H minus, and let's now focus on E0, the ground state of the system. And the equation which we are looking at is this one. If you can diagonalize, you have the coefficient C immediately. No, like that. So this is the Schrödinger equation where we just have pulled over to the left-hand side this equation. Now the first row of the problem which we looked at is given by us multiplying is given, oops, my writing here is not the best one today. First row is given by multiplying from the left with phi 0. So let's do that. And I'm going to use, and we're going to use, and we will use the intermediate normalization for simplicity and use that C0 is equal to 1. So if I now do that, let's just write out what we are going to get here. So we will get now phi 0. We are just multiplying out. And then I have Hamiltonian minus E0. And then the first term in the series expansion, which we have here, is obviously phi 0. That's the first term here. Then the next term has to be phi 0. And then I have a sum here over these particle hole states. So there's a one particle, one hole excitation, H minus E0. And then I have a phi of IA times CIA. Then I get a new term, which now contains the two particle, two hole excitations. But then after that one, there's something interesting which comes into play. And I'm going to set that up soon, AB. And then I have a CIJ, AB. Now remember now that if you look back at the Hamiltonian matrix we put up, since then, if we think of the next term, which will be a free particle, free hole excitation, then we have more than one, we have three single particle states which differ from the bra side. And that means that that has to be equal to 0, which is actually what we found here. So that means that when I perform this multiplication, this series terminate at the level of two particle, two hole. And this is just equal to 0, right? Now, if you then look at some of these terms, if you look at this specific term here with that one and this one, that has to be 0 because this is a constant and this is a constant. And then we have the overlap between two states which are orthogonal to each other. And similarly with E0 here, I have now the overlap between this state and that state multiplied by a constant, and that has also to be equal to 0. So these terms here with E0, I can just leave them out. So what I'm going to get then, if I now put everything together, I'm going to get a term which gives us phi 0, and then I have the Hamiltonian of the system. And this is something which we have calculated before, and we call this a reference energy. So remember now that when you have a basis which you have chosen, one of the kind of main motivations behind choosing that basis is that this allows you to calculate in a speedy way or an easy way this specific expectation value. So this is something we assume we have calculated, and it's the vacuum or the new reference state energy. But then we have now the next term, which then obviously contains phi 0 times the exact energy, E0. So this is the exact energy which we are looking after. We don't know that one. But then it contains a new term where we have AI, and then we have the phi 0 state, and we have the Hamiltonian now, and phi AIA of CIA plus an ABIJ phi 0 of H and this has to be equal to 0. Now we have already calculated these terms, and we know exactly that this one has a form which goes like I, and it's the integral over this new operator F, And here we have IJ, V, and AB. And this is anti-symmetrized. So we know these integrals. And if we have tabulated them, we can look up in a table immediately, or we can calculate them on the fly. So if I now rewrite everything, we have an expression for E0. So what I'm going to do now is actually to bring this and this term over to the other side. So what I'm going to get now is something I will call the correlation energy, delta E, or the ground state. So this term here is the correlation energy, where you have the contribution from the mixing of your ansatz for the ground state with the other states. So this is called the correlation energy. And for a two-body interaction, this really simplifies. So it's E0, the true value, minus this reference energy, which we can calculate. So this difference can be sometimes pretty minute in case this reference energy is close to the exact value. Or it can be a huge number, which means that then you need to labor a little bit more. So we would now have a sum of I and A, and we can look up this integral here. And then we have the unknown coefficient CIA. These are unknown. If you diagonalize, you obviously have them. So plus AB and IJ, V, AB. And I'm going to skip this anti-symmetrization sign. And this is the expression for the correlation energy. And with a two-body interaction, this summation over configuration stops here. So if we can diagonalize, so we would have this one and that one. So they are known from diagonalization. If you can diagonalize, diagonalization. So what I've done here is actually to write in a very stupid way the energy for the ground state. Because when I diagonalize, I obviously have E0, right? So there's no point in doing in this exercise. But the reason why I bring in this exercise is that this simple equation here is going to allow us to set up another way of finding the eigenvalues. And you can do that by iteration. There is another thing which is interesting here. And I'm going to mention this before we have derived the mean field methods. So let's just single out this one. So if I do something which is called Hartree-Fock theory, that means that these integrals are going to be exactly equal to 0. So that term disappears. Now, this is something which we will start looking at tomorrow, and we're going to set up the equation. So this is one of the more famous mean field methods. And for those of you interested in, let's say, mean field methods like density functional theory, this is actually the first stepping stone. And we will start looking at this method tomorrow. This obviously simplifies the equation, but there's a reason why I also bring up this type of interpretation or this type of aspect, because if you go back to the Hamiltonian matrix, what that means is the following. So can I shift to the next page? Is that okay? Or not yet? Okay, let me just wait a little bit. So if you think of setting these specific contributions equal to 0, what that means is the following. So for the Hamiltonian matrix, the consequences are the following. So I'm just setting up the matrix. So the first block, which is the reference state to the reference state, I'm now going to write this with an x tilde. And the reason for that is because what happens now is that you can think of this as a unit, as a transformation of your matrix where you zero out some specific matrix elements. By doing that, you've actually performed what we call a similarity transformation of your Hamiltonian matrix. So this is still non-zero, but then all the other ones are zero. So then here I will have zero, and then this will change. This will obviously change. This changes. This is non-zero. This is also non-zero, and these become zero. So we will have this band here again, exactly the same, where we have lots of zeros, and then we have elements which are non-zero. So what has happened now is that we have actually performed an operation on your Hamiltonian matrix where we have zeroed out some specific elements. So keep in mind that when you diagonalize, so let me remind you a little bit about the diagonalization itself. So the way you extract the eigenvalues. So ideally, when you solve an eigenvalue problem, is that suppose now that you have a unitary matrix, or it can be orthogonal if your matrix elements are all real numbers. This is a unitary matrix. We discussed that last time as well, a little bit. So this is just equal to the inverse. So if I now look at my Hamiltonian problem, so H is now a matrix, and this is multiplied by an eigenvector C, and that's given by lambda times C. What I can do now is to multiply from the right with this matrix U. So that gives us U times H times C is equal lambda, which is just a constant, times U times C. So U is a matrix. Now I can insert the unit matrix here. So I would then have U times that one. I have U mission conjugate times U times C, and that's equal to lambda U times C. I can define this as a new vector, which I can call for B. So this is B. And my matrix now, ideally, my matrix now should be diagonal. But normally, it doesn't happen in one stroke. So you will have to do this type of operations many, many times. The ideal here is that this becomes a diagonal matrix. That's the ideal. So D would then simply be a matrix where you have all the eigenvalues lambda 1, lambda 2, down to some lambda n. However, this is not achievable unless you have a 2 by 2 matrix, because then you can really set this up in a simple way. But you have many ways of finding such transformations. So the ideal thing now, so what you see also is that the eigenvalues are the same when you perform such a similarity transformation. Similarity because you keep the dimensionality of the matrix, but the matrix becomes more and more diagonal. So ideally, this diagonal matrix is going to be the result of many such transformations. So you would have up to n, so you have un minus 1, and this goes all the way to the first one, and then you have the Hamiltonian, and then you have ui, u2 here, and that goes all the way up to u of n. So you would perform many such operations. So setting this block here, phi 0 of h to the phi I of a equal to 0, corresponds to a specific u of I, which zeroes out a sub-block of the Hamiltonian matrix. And hopefully that gives a faster convergence when you're using a diagonalization algorithm. So this is one way to interpret what is coming tomorrow when we start discussing mean field methods. Because as you will see when we derive the equations for Hartree-Fock theory, that will correspond to actually setting these matrix elements equal to 0. Okay? So one thing I wanted to do now is to do something extremely clumsy for the rest of the lecture. So there's a way to solve an eigenvalue problem. Instead of using eigenvalue solvers, you can solve the problem iteratively. So if you now go back to the eigenvalue problem, what you can do is to, if you look at the different rows you have in the equation, so if we go back a little bit here to what we did here, if you look at the different rows we have written out here, so each one of these rows could then be solved iteratively by having a guess on these coefficients. So you will start with a guess 0. That's the first iteration. And then you will get a new eigenvalue. And you will get new such coefficients. Now, the reason why I'm bringing this iterative scheme up is because this links with the approximative methods we will discuss later. So let's take a look at the second row. So we wrote down the first row just now. And what we did was simply to take the expression here, this expression, and we multiplied by phi 0. That was the first row of the Hamiltonian matrix. If we now take the second row, it means that we would multiply with a one particle, one whole state. That's the second row of your Hamiltonian matrix. So let's do that and see what comes out. So what I'm going to do now is to take this expression here, because now we just produced the first row, and doing that one, we could also introduce this concept of a correlation energy, which has an exact analytical expression, a nice analytical expression, except that we don't know this one, and we don't know that one, unless we can diagonalize. So let's take the second row and take this expression here, and just multiply with a one particle, one whole state. So what we're going to do now is to look at what happens if we would like to, instead of diagonalizing the problem, to solve it iteratively. So as I said, the reason why I do this is that this is going to link with other many-body methods, which are approximations to the true diagonalization problem. So this mean field method, which I mentioned, which is Hartree-Fock theory, can be thought of as a special similarity transformation of your Hamiltonian matrix, mathematically. So let's now take and multiply with phi IA, and we take this H, the Hamiltonian, minus, we just keep E0 now, because this is the state we are focusing on, but you could have picked any other state here. And then we have this summation of a PH, we have a CHP, and then we have a phi of HP here, like that. And this is obviously equal to 0. Now we multiply with that, so we would have a phi of I, and then we have the Hamiltonian here, and the first term is phi 0. Then we get a minus E0, and phi of I, and then we have obviously phi 0. So this term has to be equal to 0, obviously. Then we get the next term, and now we're going to break it down in terms of particle hole excitations. So we have a BJ, and then I have a phi IA, and then I have H minus this E0, which is a constant, and now I have a new state. So they can be the same, or they can differ. So the subscripts and superscripts J and B do not need to be equal to I and A, but there will be a case where they are equal. Then I have plus, and then I have the B, C, and J, K. I have the same guy here, IA of H minus E0, and then I have a phi of JK and BC. There's a coefficient CJK, BC, and this stops at the level of free particle free hole excitation, JKL. So this starts looking ugly now. C, D. And then we have the coefficients J, K, L, B, C, D. And this obviously has to be equal to 0. So if you now write things out, we know very well that this one is something which we calculated. So this has now to be equal A of F of I. So we have that one. This is something, this is known. This is obviously equal to 0. And then we can single out different terms here. So let me just look at this term here. And then I'm just going to put this one as a set of new terms. So if we now write it out, this is probably the last thing we're going to get to do today. But just wait a moment so everybody can write down correctly. If we do that, then what I will get now is this term A of F of I. And now I'm going to pick a term here where J and B are the same as this one's, because then I will also get a term with E0. So I will have a plus. There's going to be a phi I of A of H minus E0. And then I have a phi I of A. And then I have a coefficient CIA. And then I have a next term, which now contains phi A. And then I have B of J, different from I and A. And then I have H. Now they are different, so E0 doesn't contribute. Plus 2 more, which I'm just going to leave out. And this has to be equal to 0. So what I can do now is to make an approximation. If I want to solve, you see this, you can actually set this up, this set of equations. What I did here was to set it up for the second row. Now, if you do it for the first row and the first and the second, if I do the third row, I will have a 2-particle 2-hole state, which is multiplied from the left. And what you would get then is just a rewrite of your equations in terms of the unknown coefficients, CIA, whatever. This lays the foundation for you solving this in an iterative way, where you start with a guess for these coefficients. Now, if you do that, then you can start iterating these equations. Because when you're iterating, you have on the left-hand side an equation here, which has to be equal to 0. So that is you finding the roots of an equation. And then you can use something like Newton's method or similar methods to find the roots of these equations. But every line which you have, when you multiply it out, gives you an equation to be solved. This is an extremely inefficient way of solving a diagonalization problem. However, it's going to give us some insights which we can use later. So if I now make an approximation here, if I now say that this term, I just put that to 0. I assume only now that the CIAs from the diagonal term are the ones which I start iterating with. I could actually have a guess here as well for that one. But if you now look at the equation, I would then have A of F of I, and then I have plus this term here, phi of I of A, of H, of phi I of A, of CI, A. And this is equal to this coefficient CI, E0 times CIA. Now, one approximation which is made, if we now look at these terms which we have here, this one minus this one, that is actually proportional to the reference energy. So if I take these two, this one and that one, which I have here, that is going to be the reference energy plus a particle Hall state. So if I bring this term as well over, what I will get, and I will show you that later, that this becomes equal to the Hall energy minus the particle energy times this coefficient CIA. That means that I have left out the other terms. And that means that this first ansatz you could make is actually given by this integral. And you see that this becomes dimensionless because it has energy divided by energy. So these coefficients are dimensionless. And this is where we're going to stop today. But what I wanted to say is that when we are going to discuss many-body perturbation theory, this is the approximation to these coefficients to second order in perturbation theory. So we can rederive order by order in a perturbative expansion the values of these different terms. So you could start an iteration now where you simply say that my zeroth value is equal to this one. But then you would have to do the same for the 2-particle 2-hole, 3-particle 3-hole, etc., etc. This becomes very, inefficient, but we are going to come back to this type of equations when we now look at many-body perturbation theory and copper cluster theory, because then you have a recipe by which you can actually find these coefficients in an alternative way. When you diagonalize, you get them immediately. The diagonalization gives you these coefficients. However, the matrix can be so big that is not practical to diagonalize. And then we need methods where we can find approximations. So if I do this kind of a cheap way of finding a first iteration where I zero out like this term and all the other ones, then I can find an expression for this one, which is going to be the same as we will get when we do many-body perturbation theory. So the whole thing now is that different methods are going to recover in different ways the coefficients which we can get. That means these coefficients which we have here, let me just bring it back, these coefficients, we can get them by approximative methods. But that means that there will be approximations. And the different many-body methods we will discuss, like copper cluster theory, many-body perturbation theory, and if we get time, some Green's functions, they are going to represent approximations to these coefficients, which we could get if we could diagonalize. So as I said, if you can diagonalize, you solve the problem. And or FCI, or full configuration interaction theory, is actually the simplest possible many-body method we can think of. If you can set up the different matrix elements and diagonalize, you have solved the problem. But the reason why we don't use it in all cases is simply because the problem has a too high dimensionality. And we need to find ways to reduce the dimensionality in the system. So I hope you start seeing the wood for the trees, because this is the simplest possible way we can set it up. And it's a matter of structuring the matrix and diagonalizing. And as I mentioned, when you are setting up these different terms here, like these ones, what you typically would do is to have bit strings of words represented by bit strings, which then represent whether you have a state which is occupied or not. And then you would simply compare bit strings. And if they differ by more than 2 bits, then with a two-body interaction, they're automatically 0. So it's very easy to actually set up an algorithm which finds out which elements are non-zero. And the matrix in general is going to be sparse. So you would often end up with sparse diagonalization algorithms for solving this type of problems. Okay, so tomorrow we're going to wrap up a little bit about this. I'm also going to represent these different terms in terms of diagrams, because that gives a very compact way of writing them down. And then we are going to move into mean field theories, which is our first approximation to the full problem. So if we can set up the full basis and diagonalize, we have solved the problem. Okay, let's stop here. Huh?